Hello. In the last lecture, we have defined principal curvatures and principal direction. In this lecture, we will find principal curvature and principal directions for some known regular surfaces. Let us begin. So this lecture is about examples corresponding to principal curvatures and principal directions. Okay. Let us first take hyperbolic paraboloid. So what is hyperbolic paraboloid? It is given by the equation z equals to y square minus x square. So if I draw the paraboloid in R3, it looks like this. And let us take this point, which is my origin. And also let us draw the axis. This is my x-axis, so this is y-axis, this is z-axis. So we'll be finding principal curvatures at the point P, where this P is origin. So let us take a parametrization of this hyperbolic paraboloid. So let sigma u be, so this is equal to u comma b comma b square minus u square. So sigma of 0, 0, it is origin. So it is the point P. Okay. So now we'll be giving the normal to the surface. The normal to the surface at the point P, it is given by n ub is equal to the cross product of sigma u with sigma b divided by norm of sigma u cross sigma b. Okay, so now let us compute this normal. So what is my sigma u? So sigma u is given by 1 comma 0 comma minus 2u. Sigma b is equal to 0 comma 1 comma tb. And now if I take the cross product of sigma u with sigma b, so that will be equal to the following: 2u comma minus 2b comma 1. and norm of sigma u cross sigma b. So this is equal to root over 4u square plus 4b square plus 1. Therefore, the normal vector at the point sigma ub is given as follows, equal to sigma u cross product with sigma b divided by norm of sigma u cross sigma b. So this is equal to twice u comma twice b comma 1 whole divided by root over 4u square plus 4b square plus 1. Okay. So now we need to compute the derivative of this map or differential of this n. So let us take a curve alpha t is equal to sigma ut comma vt. So this alpha, it is a curve in this surface such that alpha 0 is equal to p, alpha t is equal to sigma ut comma pt, and alpha 0 is equal to p. And we know the definition of this sigma. So therefore, this alpha t is equal to ut comma vt minus vt square minus ut square. Now, let us compute this alpha prime t. So this is u prime t comma v prime t twice vt v prime t minus twice ut u prime t. And alpha prime 0 will be equal to what? Okay, so first note that so alpha 0 is equal to p is equal to 0, 0, 0. So this implies that u0 equal to v0. Okay, sorry, not this one. Yeah, so u0 comma v0 comma v0 square minus u0 square. So this will be equal to origin. So in particular, u0 is equal to 0 and v0 is equal to also 0. So now, so this alpha prime 0, so this will be equal to u prime 0 comma v prime 0, and v0 is equal to 0 and u0 is equal to 0. So therefore, the third coordinate of this alpha prime 0, it will be equal to 0. Now let us compute dnp of alpha prime 0. So this will be equal to limit t tends to 0 n alpha t minus n alpha 0 whole divided by t. So this will be equal to limit t tends to 0. So n of alpha t, so this will be equal to the following. 1 by root over 4 ut square plus 4 vt square plus 1 multiplied by twice ut comma twice vt comma 1 minus n of alpha 0. So this will be equal to 1 by root over 4 u0 square plus 4 v0 square plus 1 multiplied by this vector 2 u0 comma minus 2 v0 comma 1. And again, this will be equal to limit t tends to 0. Yeah, so in the above, so this whole thing is divided by t. Yeah. So this will be equal to limit t tends to 0, 1 by t multiplied by uh, 2 ut divided by 4 ut square plus 4 vt square plus 1 comma 2 vt divided by root over 4 ut square plus 4 vt square plus 1 comma 0. Yeah, so here again note that this u0 is equal to 0 and v0 is also equal to 0. So therefore, this will be equal to the following. So this t, now you can take it inside. So it will be twice ut by t divided by this root over 4 ut square plus 4 vt square plus 1. The second coordinate is also the same. So now if I take the limit t tends to 0, so what you will get? So it is equal to twice u prime 0 minus twice v prime 0 comma 0. So again, I'm using this fact that u0 is equal to 0, v0 is equal to 0. So note that here in this expression, if I take this expression, limit t tends to 0. So in the numerator, it will be u prime 0, and in the denominator, u v are continuous functions. So ut will tends to u0, which is equal to 0. So therefore, the denominator as t tends to 0, it will be equal to 1. Okay. So therefore, we have computed this dnp alpha prime 0, and alpha prime 0 is equal to u prime 0 comma b prime 0 comma 0. So therefore, this dnp of this u prime 0 comma b prime 0 comma 0, it will be equal to twice u prime 0 comma minus 2 b prime 0 comma 0. Okay. So we got this thing. So now let us take these two curves. So let us take this alpha 1 t to be equal to sigma of t comma 0. So which is equal to t comma 0 minus t square, and alpha 2t is equal to sigma of 0t, which will be equal to 0 comma t square. Okay. Let me draw the picture of the hyperbolate again. This is my x-axis, this is y-axis, and this is z-axis. Okay, so now what is my alpha 1 t? So alpha 1 t is like this. So this is my alpha 1 curve. And what is my alpha 2 curve? It is this curve, alpha 2. Okay, so now, so what is my alpha 1 prime 0? So this is equal to 1 comma 0 comma 0. And alpha 2 prime 0 is 0 comma 1 comma 0. And this t and p of this 1 comma 0 comma 0, which is equal to dnp of alpha 1 prime 0. So this will be equal to dnp, not dnp. So this will be equal to twice of this uh, of the derivative of the first coordinate of this alpha 1 at the point t equals to 0. So which is just equal to 2. So it will be, so dnp of 1 comma 0 comma 0, it will be equal to 2 comma 0 comma 0. Okay, so which is equal to 2 1 comma 0 comma 0. And dnp of 0 1 comma 0, which is equal to dnp of this alpha 2 prime 0. So this is equal to, by this formula, so this will be equal to 0 minus 2 comma 0. So which is equal to minus 2 times the vector 0 1 comma 0. Okay. So therefore, 1 0 0 and 0 1 0 are the eigenvectors of DNP with eigenvalues 2 and minus 2 respectively. Okay. So now, so note that, so what will be the maximum curvature and what will be the minimum curvature? So this curve alpha 1 at the point P, so it will give the minimum curvature, so that is equal to minus 2. And this alpha 2, this curve, if I take the normal curvature of this curve alpha 2 at the point P, so this will give the maximum curvature, maximum normal curvature. Okay. So maximum normal curvature at P is 2 and it correspond to the curve alpha 2 with principal direction 0, 1, 0. And the minimum curvature, minimum normal curvature at P is -2, and it is along the curve alpha 1, and it corresponds to the curve alpha 1 with principal direction 1, 0, 0. Okay. Go back to the picture of hyperbolic paraboloid. So here, the normal at the point P is 0, 0, 1. And we have these two curves, alpha 1 and alpha 2. So this curve alpha 1, it bends away from the normal NP, and alpha 2, it bends toward the normal. Okay. So this bending of these curves, so this will help to determine the notion of curvature of a surface. Okay, so now let us take another example. Let us take this sphere in R3. Okay. First, let us draw this sphere, unit sphere in R3. And now if I take any point x, y, z, so this normal to this sphere, either it is in the outward direction or it is in the inward direction. Okay. So n of x, y, z either it is equal to x, y, z, or it is equal to minus x minus y minus z. Okay, so we can take two orientation of this unit sphere S2. So one is outward normal and another is the inward normal. Okay, so let us take nxy z is equal to minus x minus y minus z. And from this, if you compute the differential of this n at any point P, where this P, it belongs to S2. So dnp B will be equal to minus B. So for all P in S2 and for all B belonging to the tangent space of S2. Okay, so this shows that, so matrix of dnp is minus 1, 0, 0, minus 1. Okay. So this eigenvalue of this matrix, eigenvalues of the matrix of D and P is R minus 1. Okay, both the eigenvalues are same and they are equal to minus 1. Okay. And note that, so any direction if I take, so any direction is principal eigen vectors. Okay, so what do I mean by this thing? So if I take this sphere and let us take this point x, y, z. So this is my n, x, y, z, this origin. So n, x, y, z is equal to minus x, minus y, minus z. And now if I take the tangent space at this point, x, y, z, so if I now take any direction on this tangent space, means if I take any tangent vector at the point x, y, z, okay, suppose this is my P, so D and P of P is equal to minus P, where this P is x, y, z, and P, it belongs to the tangent space. Okay, so therefore, so any direction in the tangent space, so it will be the principal direction. Okay, so any direction is principal direction. Okay, and so what will be the normal curvatures? So normal curvatures at P are R minus 1. Okay, so why this is minus 1? Because pi P of P is equal to minus D N P P comma P. So this is equal to minus of minus B comma P, which is equal to 1. Yeah, so sorry. So the normal curvatures at P are in fact here 1. Okay. Okay. So therefore, if I take any curve in the sphere passing through this point P equal to xyz. So this curve, it bends towards the normal. So if I take any other curve in this sphere passing through this point, so normal to, so this curve, it bends toward the normal. Okay, all the curves, it bends towards the normal. Okay, so later on, we'll be describing Gaussian curvature. So we'll see that, so the Gaussian curvature of sphere is positive, whereas in this hyperbolic paraboloid, because of this phenomena that one curve is bending away from the normal and another curve is bending towards the normal, the Gaussian curvature of this surface, hyperbolic paraboloid at this point P, it will be negative. Okay. Now let us do another example. So let us take the plane. So let P be the plane AX plus BY plus CZ equal to D. So what will be the normal to this plane? So this is a plane in R3. So the normal to this plane, it is given by, so nxyz is equal to 1 by root over a square plus b square plus c square whole multiplied by a, b, c vector. Okay. So this is my normal to the plane, and this is a constant map. So therefore, dn xyz, so this is a zero map. Okay, so this is a zero map. So this implies that normal curvatures are zero. Okay. Now let me give you final example. So this of cylinder. So the equation of the cylinder C is given by x square plus y square equal to 1 in R3. And let us take this normal unit vector field. So again, on cylinder, I can have two choices. So nxy z equal to xy 0 or minus x minus y comma 0. So the first one is outward normal unit vector, and the last one is inward normal unit vector. So let us take, so let nxyz equal to x comma y comma 0. So then, so d and p of p is equal to 0. So if b is parallel to z-axis and d and p equal to b, so if b is parallel to xy plane. Okay. Okay. So this implies that eigen values of this linear map DNP are 0 and 1. The eigen vector corresponding to to 0 is 0, 0, 1, and the eigenvector corresponding to 1 at the point P equal to P1, P2, P3 belonging to the cylinder is P2 minus P1, comma 0. So we have this cylinder and suppose this is my point P. Okay. So the eigenvectors corresponding to 0, it will be this unit vector, vertical unit vector 0, 0, 1. Okay. And the eigenvector corresponding to the eigenvalue 1, it will be equal to this tangent vector B, which is parallel to xy plane. Okay, so now you have to find this B, which is also a unit vector. It starts from the point P and it is parallel to xy plane. So you know that coordinate of P is equal to P1, P2, P3. The center of this circle, so it will be 0, 0, P3. So therefore, this vector, it will be equal to, so this vector, it will be equal to P1, comma, P2, comma, 0. And P2, comma, minus P1, comma, 0, it will be orthogonal to the vector P1, P2, comma, 0. And so this B vector, it will be in fact P2, comma, P minus P1, comma, 0. Okay. So the principal directions, the principal directions are given by 0, 0, 1 and P2 minus P1, comma 0 at the point P1, P2, P3. Okay. So now, observe this thing. So you have this cylinder. And this is my, say, point P. So the normal to the surface cylinder is given as follows. So NP is this. So we have taken the outward unit normal vector, and we got also the principal directions. So one principal direction is parallel to z-axis, and another one is parallel to xy plane. Okay, so we got this principal direction. And now if I take this vertical line passing through the point P, okay, so this is just a straight vertical line. So this doesn't have any bending towards the normal or away from the normal. Okay, so that's why the normal curvature of this curve at the point P is 0. Okay, and now if I take this circle passing through point P, so this curve, which is circle, it bends away from the normal. Okay, yeah. So the Gaussian curvature, it will be defined to be the product of the principal curvatures. So here one principal curvature is 0 and another one is positive, and when you multiply it will be equal to 0. So the Gaussian curvature of the cylinder, it will be defined to be sorry, so Gaussian curvature of the cylinder, it will become to be 0. Okay, okay, so we'll continue in the next class.